Okay, so for our first review lesson, it's going to be on the real number line and the properties of real numbers. So before we actually talk about the real number line, we're going to talk about the real numbers as a set of numbers. So let's first define what a set is. So a set is a collection of objects, and each object that's in a set is called an element. So if we're talking about a set of numbers, each number that belongs to the set is an element of the set. Okay, I've put an example of a set on here where if we think about Pinewood's upper campus as being a set of different grade levels, 7th, 8th, 9th, 10th, 11th, and 12th grade, then each grade is going to be an element of the Pinewood Upper Campus set. Now, within the set of Pinewood's Upper Campus, we also have what we call subsets. So a subset is a set consisting of elements that belong to a given set. So basically where a set is a subset of another set if each element that belongs to that set also belongs to the other set that we're saying it's a subset of. So like if we have Pinewood Upper Campus, which is grades 7 through 12, and we're referring to each grade as being an element of the set, we can say that there's a junior high subset, which would include 7th and 8th grade. We could also say there's a high school subset, which would include 9th, 10th, 11th, and 12th grade. Then within that high school subset, we could even break that down even more and say, okay, well, there's a lower classman subset, which would be 9th and 10th grade, and then a upperclassman subset, which would be 11th and 12th grade. But a set is a subset of another set as long as each of the elements that belongs to that set also belong to the other set. Okay, so we are going to be talking about the real numbers, the set of real numbers where each element is a real number, and then all of the subsets of the real numbers. And we're going to start with the most basic subset of the real numbers, which are the natural numbers. And the natural numbers are also sometimes referred to as the counting numbers. And that's because they're 1, 2, 3, 4, 5, 6, 7. So the numbers that you could just keep counting on your fingers if you wanted to. Now, notice that I have the set of natural numbers represented here. I have the curly brackets to imply that it's a set of numbers. And notice that there are 3 periods after the 5. And that's referred to as an ellipsis, and it indicates that the numbers will continue without bound. So 1, 2, 3, 4, 5, 6, 7, 8, and so on. There's no way that ... means that there's going to be infinitely many elements that belong to this set. There's no way that I could ever write down all of the natural numbers. Okay, and then just a special note that 0 is not included in the set of natural numbers. Now 0 is included in the whole numbers. Okay, so the whole numbers are all of the natural numbers, so 1, 2, 3, 4, 5, 6, and so on, and also 0. So 0 is included in the whole numbers. Now, the natural numbers we refer to as a subset of the whole numbers because every number that is a natural number is also a whole number. However, the whole numbers are not a subset of the natural numbers because 0 is not a natural number. We need to be very careful though with the adjectives that we use to describe these sets and their subsets, because remember, there's infinitely many elements that belong to the natural numbers. There's also infinitely many elements that belong to the whole numbers. So we can't say that the whole numbers, even though the natural numbers are a subset of the whole numbers, we can't say that the whole numbers are a larger set, okay? Because there's just infinitely many numbers that belong to each of those sets. Now, the natural numbers and the whole numbers are subsets of the integers. So the integers are made up of the natural numbers, 0, and then the opposites of the natural numbers, okay? So like -3, -2, -1, 0, 1, 2, 3. And you can see that we use the ellipsis, that ... on each side, on the left side and the right side of this list. Okay, so whenever we use the ... on the left side here, it means that this list of numbers is going to continue in both directions. It's going to continue to negative infinity, and the ... on the right means that the list will continue to positive infinity. Okay, so again, there's infinitely many elements or infinitely many numbers that belong to the integers. Okay. And again, the natural numbers and the whole numbers are both subsets of the integers, because every natural number is also an integer and every whole number is also an integer. However, the integers are not subsets of the natural or the whole numbers, because -1, -2, -3, so on, are not whole or natural numbers. Oops, make that go away. All right, so the rational numbers. So the natural, whole, and integers are all subsets of the rational numbers. Okay, so the rational numbers, notice that in the word rational we have the word ratio. So the set of numbers that can be written as fractions, whose numerators and denominators are integers, are referred to as the rational numbers. So the rational numbers can be written as a ratio. Now, not every, you don't always see a rational number represented as a fraction necessarily. Sometimes you'll see them represented as decimals, but those decimals that are rational numbers can actually be rewritten in fraction form. For example, 2.3, we can rewrite 2.3 as 23/10. Okay, so a rational number is a number that can be written in the form a/b, where a and b are integers, and b cannot be equal to 0. Okay, remember, we cannot divide a number by 0. And a rational number is a number that can be written as in decimal form as a terminating decimal. Okay, so an example of a terminating decimal could be like 0.5 or 2.758, okay? But where the decimal stops, you can see the entire number. A rational number can also, in decimal form, be an infinite repeating decimal. So another word for infinite would be a non-terminating decimal. So a decimal that continues on forever is infinitely many digits. Oops, switch back to the pen. And an example of an infinite repeating decimal would be like 0.66666 repeating, right? Or 0.333, like 1/3, 0.33333 repeating. It can also be something like 1.123. And if I put that line over the 1, 2, 3, it means that 1, 2, 3 repeats forever. So 1, 2, 3, 1, 2, 3, 1, 2, 3. Or it can be something like -5.7 9, 8, where maybe just the 9, 8 repeats over and over and over again. Okay, so it's non-terminating, goes on forever, but has a repeating pattern. Okay, so the rational numbers are a subset of the real numbers. Okay, we're kind of going through all of these subsets of the real numbers to help us define what a real number is. And then the integers are a subset of the rational numbers. The whole numbers are a subset of the rational numbers and the integers. And the natural numbers are a subset of the rational numbers, integers, and whole numbers. Okay, so now let's talk about the irrational numbers. So a number can never be both irrational and rational. The irrational numbers are a subset of the real numbers, but all of the other subsets of the real numbers that we've talked about are not subsets of the irrational numbers. So the irrational numbers are defined as any number that cannot be written as a ratio of two integers. So kind of the opposite definition of what a rational number is. And they can be written as infinite, non-repeating decimal numbers. So a famous irrational number is pi. There's also E, which is Euler's number. It can be approximated with 2.71 is another famous irrational number. Square root of 2 or the square root of 3. Basically, the square root of any non-perfect square. I have 5.67345298 ... where that ... remember, implies that the decimal will continue on forever. Notice that there is no line to indicate there's any sort of repeating pattern. So this is a non-term 5.67345298 ... is a non-repeating decimal, and it continues on forever, so we say that it's either infinite or non-terminating. Okay, so the set of real numbers is defined as the set of all rational numbers combined with the set of all irrational numbers. So we have this little picture here, okay, to help us see. So basically the real numbers are just made up of the rational and the irrational numbers. And then we have these different subsets of the rational numbers. Okay, for your homework, you guys are going to be asked to classify different real numbers that I give you. All right, so the real number line allows us to visually display real numbers by associating them with unique points on a line. So you can represent all different types of real numbers, whether they're rational or irrational, on the real number line, and it can kind of give you an idea of how they relate to each other. So for example, if I wanted to put the integers on here, I could put 1, well, I'm actually starting with like the natural numbers, right? 2, 3, or the whole numbers since 0 is there. So 3, 4, 5, 6. That arrow implies that the number line continues on forever. And then I go to the left of 0 and include the opposites of the natural numbers. Now we can look at this number line and say it represents the integers. Okay, and I can also include like some of the rational numbers, like this would be 1/2, 3/2, okay, and maybe some of the irrational numbers. So pi can be approximated with 3.14, so like pi would be just past the 3. Okay, the number E, Euler's number, is 2.71, so it would be just to the left of 3, and so on. But it's a way that we can visually represent the real numbers. Okay, so next we're going to talk about the properties of real numbers that you should be familiar with. And these properties are important because they come up a lot, actually. Whether we are solving equations or if we're doing some sort of derivation, we often will be applying these different properties. And these properties are true for any real number. So for all of these properties, the way that I have them written, you can assume that A and B, and if I also use C and D, that they're all real numbers. So we're going to start with the commutative property, and we have a commutative property for addition, and we have a commutative property for multiplication. So the commutative property for addition says that A plus B is equal to B plus A. So the terms flip-flop. So an example would be like 3 plus 8 is equal to 8 plus 3. Now notice that there is not a commutative property for subtraction, and that's because, like, if we had 2 minus 3, that is not equal to 3 minus 2, right? 2 minus 3 would be negative 1, whereas 3 minus 2 would be positive 1. But if we had something like 3 minus 2, that could also be thought of as 3 plus negative 2, which then, applying commutative property, that's equal to negative 2 plus 3. Okay, so anytime you think of subtraction, you could also think of it as addition, where then the commutative property does hold. And then multiplication, it's the factors flip-flop. So A times B is equal to B times A. So like 7 times 5 is equal to 5 times 7. Now, students tend to mix up commutative and associative property. And I'll explain the way that I kind of keep them straight in a second. So like the commutative property, the associative property has the associative property for addition and also the associative property for multiplication. And the associative property for addition says if we have A plus the quantity A plus B plus C is equal to A plus the quantity B plus C. So for example, if I have, I don't know, say 2 plus 3 plus 4. And I group together, or I like to think of it as reassociating 2 plus 3. That's going to be the same. The left-hand side is going to be the same as if I were to group together 3 plus 4, those two terms. Okay, in thinking order of operations, which we will review soon, 2 plus 3 is 5, plus 4 would be 9. Over here, 3 plus 4 is 7, plus 2 would also be 9. And then for multiplication, it's a similar idea, but if we had like 2 times 3 times 4, okay, and I group 2 times 3 together, that's going to be the same as if I were to group the 3 times 4 together on the right-hand side. Okay, so for commutative property, notice that for addition, the terms move around. So the moving around, I'm thinking about them commuting. And the factors for multiplication, the factors are switching around, so they're commuting. And for associative property, whenever I'm applying the parentheses, I think about I'm regrouping or reassociating the terms with each other. Same thing, I'm reassociating the factors for the multiplication. All right, the identity property is for addition says that we can add 0 to any real number and we'll get the real number. Okay, so for example, -10 plus 0 is equal to -10. Okay, for the identity property for multiplication says you can multiply any real number by 1 and it's equal to itself. 7 times 1 is equal to 7. Okay, the inverse property for addition says that every real number has an additive inverse. And if you add the additive inverse to of a number to itself, then you get 0. So, for example, 2. Okay, the additive inverse of 2 is -2. 2 plus -2 is the same thing as 2 minus 2, which is 0. The inverse property for multiplication says that if you multiply a real number by its multiplicative inverse, which is just another word for its reciprocal, you'll get 1. So if, let's say I multiply 6 by its multiplicative inverse, which is its reciprocal, which is just 1/6, okay? 6, remember, can be written as 6 over 1. And you can think of the 6's as canceling here, this ending up as 6 over 6, which is just 1. Another example would be like 2/3 times its reciprocal, which is 3/2. Okay, just the reciprocal, remember, is the flipped fraction. Okay, that would end up being 6 over 6, or you could think of the 2's as canceling and 3's as canceling to give us 1. Now, the zero factor law says that you can multiply any real number by 0 and you'll get 0. So if 0 is a factor in a product, then that product will be 0. Let's see, how about like pi times 0 is 0? Or 100 times 0 equals to 0. Even like we could think of a variable as x, I guess a can be thought of as a variable, right? X times 0 would be 0. Okay, distributive property. So if we have a quantity time being multiplied by a sum or a difference of terms, we can apply the distributive property. So I go A times B plus A times C. It can also be like if this were A times the quantity B plus C plus D, or let's even make that, how about a minus D? You just distribute to each term. So A times B, okay, plus A times C, and then paying attention to the sign, minus A times D. Now, this, by the commutative property, okay, we could also have B plus C times A, and then to multiply or apply the distributive property is the same thing. A times B is AB plus A times C. Okay, so the multiplication symbol is optional when multiplication is between two variables or a number and a variable. And when there is multiplication between a number and a variable, the number is referred to as the coefficient of the variable. So for example, like 2x. 2 would then be the coefficient of x. Okay, or you can have multiple variables. So we could have like -3 xy. And -3 would be the coefficient. But I also noticed, because it's variables that are being multiplied, I do not need to put the dot to imply multiplication. All right, so we are going to practice identifying the property that is being demonstrated. So in A, part A, let's switch colors. In part A, notice that the order, so we have addition happening, and notice that the order of the terms is not changing. However, the parentheses are moving. So it looks like the terms are being reassociated. So this is going to be the associative property of addition. You have to be specific. Okay. Now in B, multiplication is happening, and it looks like the factors are switching. Okay, the factors are moving around or commuting. So we have the commutative property of multiplication. Okay. So we have multiplication happening in part C. And we have 15 being multiplied by 1/15. Well, 1/15 is the reciprocal or the multiplicative inverse of 15. So this is going to be the multiplicative inverse property. Okay. Still identifying the property. So 3 plus 7 equals to 7 plus 3. The terms are switching around. So this is the commutative property of addition. Okay. So here, the parentheses are going away from the left-hand side to the right-hand side. So that tells me that we are applying the distributive property. So 5 times x, 5x, and then 5 times -2 would be -10. And part C, we have multiplication. The order of the factors is not changing, but the parentheses are moving around. This is the associative property of multiplication. Okay, so for your homework, you guys will be practicing identifying what property is being demonstrated, but then also practicing being given the property and one side of the equality saying what the other side of the equality would be.